Hi, my name is Jeff Nolan. I'm the host of Now, Next, and Beyond. With me today is Dr. Sanjay Parthasarathi, Chief Marketing Officer at Coherent. We had the opportunity to sit down together in my home state of Florida for this 1 hour and 15-minute conversation, which we've broken into two podcast episodes, part 1 and 2. The list of topics is extensive. Optical networking, basics, how do transceivers work, what are the components, how do we build them? Where are we going? Like, what's the next generation of transceivers in terms of speed and performance, and how this is impacting the world of AI and the mega expansion cycle that we're in for data centers. Talked about engineered materials, what they are, why they're important, how they're made, where we're going, advanced lasers. So much there's something for everyone in this one. So thank you for joining us. Get comfortable and let's get going. Okay, welcome everyone to Now, Next, and Beyond, a podcast from Coherent. I'm your host, Jeff Nolan, and with me today is Sanjay Parthasarathi, the Chief Marketing Officer of Coherent. Welcome, Sanjay.
Yeah, thank you, Jeff. It's great to be here.
We're going to put the bios in on the speaker notes, and so I'm not going to go and burn a lot of time on that. But I do want to start by saying Coherent is finding itself at the center of some really interesting big trends. And we're going to use this episode to talk about those, to get your thoughts and feelings, opinions about where we're going as an industry and as a company. But also, how do we plan for all of this? How do you build strategy? How do you intake product plans when the market itself is changing so dynamically and in often unpredictable ways? And I was reading a separate analysis about the AI market and what's coming in 2025 to 2028, which we'll talk about later, that really could just throw a curveball into everybody's plans. Okay, at Coherent, this is clearly not a workshop-sized effort to do all of this planning, and the ability to deliver the kind of products that we require, that our markets require, takes years and oftentimes
decades sometimes.
And the invention of entirely new technologies which are not foreseeable. So, most importantly, the ability to see the emergence of things before everyone else is a key part of your job. So I'm excited to talk with you about that today. But first, I want to get to know you at a different level. So we're going to do a lightning round. What's your favorite food?
Pizza.
Really?
Yeah,
I didn't expect that.
Absolutely.
Any particular kind of pizza? Please
well,
don't
the
say
kind that you get in Napoli, that's for sure.
All right.
But it's not easy
as long
to
as
get
it doesn't have pineapple on it.
Yeah.
All right. And last one, if you could be anywhere in the world for a relaxing vacation, where would it be?
Tahiti.
Okay, those are great answers. Thank you. Okay, so let's go a little more serious on your background. So you've got a really interesting background in mechanical engineering, and I saw aerospace as well.
Sure.
And how did you end up in optical communication? Yeah. How did you get there?
It's been a journey. So I got a bachelor's in mechanical engineering from the Indian Institute of Technology in Madras, and then I got a scholarship and an assistantship. I was invited to the University of Virginia to pursue a master's in mechanical and aerospace engineering, and then after completing it, where actually I worked on really advanced materials for metal matrix composites, aerospace alloys, primarily for aerospace type applications. And then I, after my master's degree, I moved to Johnstown. My very first job was in Western Pennsylvania. I was working for a defense subcontractor, again on advanced materials, advanced material processing, everything from high temperature superconductors to metal matrix composites, the works. And it was an applied research technology transfer environment. And I was working on my PhD part-time at Penn State. So I would actually drive to Penn State, to do all that. And at Penn State, I worked on thin films. I worked on, amorphous silicon, polysilicon, a transition that generates a lot of revenue for us, right? Back in the day, we would deposit these amorphous films on substrates and then put it in a furnace to anneal it.
Yeah.
And, little I had known, I mean, this was in the mid to late 90s. Little had I known I can do it with a laser, which is what we do today. Display OLED stuff is all that transition generates billions of dollars for us. It has generated. After finished my PhD, I was recruited to the Silicon Valley by Western Digital, where going from R&D to here, I was running basically process engineering for disk drives, high volume, 24/7, high tech production environment. So here, a guy from R&D goes all the way to the other end. I'm woken up at 2 a.m. in the morning to solve production issues. Hey, we have a fire on the line, or we have this in the line. It was quite a big change. And then staying in consumer electronics, I went to Terrastor, where we are doing a removable optical drive. And in addition to managing that development process there, I was responsible for managing relationships with our partners. These were companies, large companies in the US and in Japan. So many of my R&D friends said, that's Sanjay, that's where you move to the dark side.
Yeah.
Because this was managing the soft side, talking about getting them enthusiastic about the market, the prospects, in addition to conveying what's going on in the development process. So that I did that for a couple of years. And then in 2001, I landed in optical communications. My very first true marketing job was in 2000, not 2001. I was director of European marketing for a company called Uplink Communications. And then in 2003, I went to Avanex, which was also an optical networking manufacturing and pure fiber optic communications. But I did marketing, and over the years, I ran pretty much one of the largest product lines at Avanex. So I was managing that for quite some time. And, long story short, acquisitions, divestitures, finally II-VI ended up picking up parts of that business. So if you look at my paycheck at my seniority date is 2003.
Yeah.
Even though we came into II-VI in 2013. So at II-VI, I ran product marketing and strategy for our largest, at that time, the photonics segment, which is our largest segment. And then in 2019, while we are getting ready for the Finisar acquisition, II-VI transformed itself. It was a transformative acquisition. We went from business units to functional structures with segments. And while we're getting ready for it, in July, I was nominated and promoted to be the first chief marketing officer for the company. So that was pretty exciting. It's been 10 years of learning and experiences and all that, and I've continued on from that point of time. So it's been close to 5 years.
Yeah.
So the one interesting snippet is, at Coherent now we have multiple market groups. We have industrial communications, electronics and instrumentation, and within each of these market groups, we have multiple verticals. And I've got sort of the dubious distinction of working on pretty much all of them.
Yeah.
Which is kind of, dabbled with some, but serious work on the others. But it's been great to kind of connect, right? I mean, I told you the display story, right? It's like, the first time I heard about OLEDs and that processing using the excimer laser, I go, wow, that's something I worked on.
Yeah.
So there are a lot of those laser processing materials. I mean, I worked on laser processing materials and concurrent technologies. And of course, over the last 20 plus years in fiber optics communications, which is bulk of our business.
Whenever I meet people in the photonics industry that have a mechanical engineering background, that catches my eye, because when I first joined Coherent, I didn't have experience in this industry, but I also didn't appreciate how photonics really is equal part mechanical engineering and physics. And as you get more of an appreciation, you see the inside of a laser, you realize there's a lot of really precision manufacturing that goes on. Also on the display topic, that one's another fascinating example, because I remember we were talking with the optics team, TEOS, up in Richmond about the JWST, the James Webb Space Telescope mirrors. And the question was, so we built these mirrors for this amazing generational space telescope, but then so what? What's next? And the team, Brandon told me, he said, the thing was, we had to figure out how to make those mirrors, which is entirely a mechanical process. He said, once we learned how to do that, then the jump was to excimer lasers for displays, for the optics.
We make optics.
Yeah.
We make cylindrical lenses.
The tubes. And he said that actually was that jump started the whole OLED revolution by 10 years because of the JWST. So it really goes to the impact that as much as, in the technology industry, we talk a lot about the abstracts, the physical world of connecting things together and making stuff is very much at the core of what we do.
Right. No, it's kind of fascinating, right? On one side, you see large mirrors, right? The JW, the Webb telescope, these are huge mirrors. I mean, we had them in the display, and I'm sure a lot of people seen it. And we also have at the other end of the spectrum, we have micron-sized
1 micron
optics.
1 micron optics.
Optics, right? 1 micron optics is refers to wavelength, but these are like tens of microns of optics. And we've got these, ultra compact, whether it's fiber optics, communications, transceivers, or line systems, you've got ultra compact form factors where there are 200, 300 optical elements, and light has to go through them and bend and diffract and do things.
A VCSEL.
It's
a VCSEL is the size of smaller than
yeah. I mean, where's my phone? My phone's not around, but hundreds of them, thousands of them in that little tiny window. It's pretty fascinating.
So when I meet someone who has the experience that you do, I always want to, I'm always curious to know like milestone developments, not for Coherent, but like things that you have seen in your career. What are some of the standout moments where something happened, you were like, wow, this changes everything?
There's so many. I'm going to try and recollect a few. I think the first one is advanced materials. Back in grad school and in Concurrent Technologies Corporation, we're working all kinds of, just amorphous silicon. I mean, displays, flat panel displays were just coming out. We had CRT tubes in our labs, right? And we say, wow, if you can deposit amorphous silicon, low temperature process, so you can put it on plastic potentially. Yeah. I mean, now we have roll up, LED screens, and we have foldable phones. But that, at that time, wow, if you could do that and then you anneal it, some sort of a low temperature, with a process that is, laser is fantastic because it doesn't heat up the process. It doesn't heat the substrate. It doesn't melt the substrate, right? So you can actually deposit it on flexible films. That was kind of groundbreaking. Whether it is metal matrix composites, diamond. We make diamond windows for the EUV tool. If you're a design engineer, as a mechanical engineer, as an electrical engineer, if you want to choose a material that has superlative everything, it's diamond.
Yeah.
It's hard to make and it's expensive. Anything, and whatever properties. So there's some amazing material science, metal matrix composites that we use in our semiconductor capital equipment, for moving to make things lighter, stronger, and really, the ability to move things around very quickly. When in the semi-cap tools, you want to move the wafer in, you don't want it to jiggle around. You want it to stop.
Yep.
Right. You want it to be firm. There are lots of, so materials is a big one. The other one is the invention of the fiber optic amplifier for communications. Without the fiber optic amplifier, basically we can't be doing this. We can't, the world's internet relies on, people don't quite appreciate the effect that fiber optics has, but because you're able to amplify light in multiple wavelengths, comes DWDM and comes fiber optic transmission. You can put terabits of capacity, hundreds of terabits, thousands of terabits through these fibers. It all started with the fiber optic amplifier. Let's see, the fiber laser. The fiber laser, it was invented in the 60s, but I think it really, was applications were envisioned and things started really heating up in the 90s. It's such a pervasive thing. Everything from LiDAR to shooting down drones to cutting metal and welding. That's another one. The iPhone 10, the first implementation of 3D sensing. That technology, AR, VR. That's another, wow. The iPhone 10 really sparked off a whole, gamut of applications, etc. 3D sensing, right? This is, it's an anonymous image, right?
Yeah.
But the photo, you've got an image that is basically cluster of points that in free space. So
intensely accurate.
Amazingly accurate.
Yeah.
Tens of thousands of points on your face. The list goes on, Jeff. I wish, you think about things and then you wait 20, 30 years and then things actually kind of come to fruition.
Well, I think
right?
it was Bill Gates who said, we we overestimate the impact of technology in the short term, but we underestimate it in the long term because
Yeah,
of the multiplier of all these
Yeah,
different technologies that come together.
That's absolutely a great quote.
Which is the AR VR comes to mind. Let's just say AR for this has been many bites at the apple, right? There's been generations of this stuff that has, been hyped up over the years. It does feel like we're kind of getting to the point where it's real now, and that is no small part because of the technology advancements that are going inside the devices themselves.
Absolutely. I mean, if you look at VR has been around for a while, and they're getting better and better, and AR is just starting to come in.
Yeah.
It's in my mind, there are maybe 2 or 3 areas. One is the sensing, eye tracking.
Yeah.
I mean, imagine, 10 years ago, you didn't have the technology to do eye track, because when you're trying to gesture, you can gesture with your eyes. Eye tracking, 3D sensing the world, sensing, the person. There is, and then displays, micro LED displays is a big deal. For these applications, I think that's coming up right now. It's mostly LCD display. The improvements in display technology, the improvements in sensing and display.
Yeah,
that's really it. And then of course you have battery technology and all of that. You don't want to keep charging it every few hours, but it's really sensing and display. It's pretty fascinating because we connect with the AR ecosystem in multiple ways. And then sensors, right? We have indium phosphide based sensors for long range, so you could see maybe even hundreds of meters. And then you have gallium arsenide sensors for short range, where you get a very high density, high fidelity image. So it's a sensing platforms.
Yeah.
And and then of course the optics, the beam, the waveguides and steering of the beam and diffractive optics. There is a lot of stuff in there that we directly intersect. It's been pretty exciting. We're working with a lot of different companies, from startups to very mature companies. It's a lot of activity there.
And on the optics side, I'm always fascinated to read more about not just what we do with the materials, but also the coatings that we develop for the optical materials, which is a whole other generation of technology that I don't think anyone could have foreseen.
Yeah, no, that's a great observation, Jeff. Coatings. We have every one of our business units pretty much has some unique coating platforms, and we just made an encyclopedia, our coatings encyclopedia. Location, what chambers, what materials, what properties. It's a book.
Yeah,
it's and the applications from semiconductor capital equipment to defense and aerospace to consumer electronics. It's pretty fascinating.
Yeah, one is the world. I mean, as we experience the effects of climate change and all the other consequences of the world, coatings that extend the life of optics or optimize the performance in less ideal conditions are going to become even more important.
Right.
So let's go. So we just talked about VR. Let's go jump over to AI because everybody wants to talk about AI. And when we first, when this topic first came up internally, part of me was like, well, okay, well, so what? I mean, so we've got optical communications and AI, but it's no surprise. It makes total sense because as these GPUs have a voracious appetite for data, you got to get it to them. So right now, current state of the art transceivers are 800G, correct?
Yeah, okay. Absolutely.
And the next jump will be 1.6.
Yes.
Okay. So
it's coming very, very soon, by the way.
It's driven by a spec process largely, right?
Sure.
Yeah.
Sure.
Yeah.
I mean,
but the technology, we know how to do it.
Yes. Yeah. We are in development now, and we will be ramping in our coming fiscal year.
Okay. So let me ask you this. So is there the speed of light constant? Is there a theoretical limit for how much data we can transmit?
Not in real. I mean, there is something known as a Shannon limit for transmission on a single fiber, but you got multiple fibers, you got multiple wavelengths. But let me, you brought up the whole AI. Let me give you a little snippet there. So in 2017, we are looking at Finisar as a potential acquisition candidate, and we're working on the deal rationale, what are the drivers, why. And Giovanni, who's our chief strategy officer and president of the materials segment, in his slide, he had AI on demand as a driver. This was 2017, 2018 one of the drivers for the Finisar acquisition. And okay, so we did not call it generative AI, but that AI and demand, the generative AI market inflected with ChatGPT in November
fast.
2022.
Yeah, really fast.
And as soon as ChatGPT happened, Chuck, our CEO, he reached out to me and said, "Hey, Sanjay, what does this mean for our transceiver business? What does it mean for our datacom business, for our communications business?" And we were scrambling because I think the speed at which AI hit the entire ecosystem, our customers are surprised, their customers are surprised. It was a rocket ship. And I think we, in March, April timeframe, we've got a fantastic team, and within the vertical leaders and within our datacom vertical, and Vipul and his team, we developed a really comprehensive view. Working with the end ecosystem, I think we probably had the first views of the AI market, as in terms of what it does to our businesses, transceivers. Everything, we are completely vertically integrated. We make everything within the transceiver, and we sell at all levels of the value chain, right? So all of that, and it was pretty good. Now we've been refining that view every few months, and you'd see that every time we kind of, oh yeah, we said that. Now actually it's even bigger than that.
Yeah.
And just in the last 3 months, we've seen the 1.6T transition hasten. It's basically come in by about 6 to 9 months. And the market, the implication for us is, of course, it represents an opportunity at transceiver because all the GPUs need to get connected. The GPUs then need to be connected to other sets of GPUs. They form servers. Those servers need to be connected. So these AI clusters, if you will, sometimes are, they look like mini data centers. There's a lot of, and all those connections have to go at highest speed because you go to ChatGPT and you type something and you're waiting for the answer, right? That wait will get lessen if you've got faster connections. I mean, that's as simple as it gets.
So Meta, I read today, Meta announced they're building a cluster of 40,000 GPUs. And how many transceivers are required for each GPU?
Oh yeah, that's a really good question. We've been this question comes up because it's easy to track GPUs, and we're trying to assess the. We started at 1.5. We believe right now it's about 1.5, but it's inching towards 2. We think it's going to be closer to 2, and that's the GPU. So every GPU you've got 1.5 to 2 transceivers. Now there's some in the industry you say that number can be as much as 8. That feels a little extreme. Yeah. I hope they're right, which means it quadruples our market size, but we think it's closer to 2 now.
And so for everybody who's listening that isn't, understands what a transceiver is, but doesn't know what a transceiver is, what components are in a transceiver?
Yeah. So think about there is the word transceiver is a hybrid word from 2 parts, right? One is a transmitter and the other is a receiver. So you've got a fiber optic link, so a pair of fibers typically. You've got data that needs to go that way and data that needs to come this way, and so you've got a laser. That's the key. The laser is at the heart of every transceiver because the laser technology paces the transceiver. So without the laser, no transceiver. Very few manufacturers of lasers are these advanced lasers. So for example, the laser that enables 800G transmission today is 100 gigabits per second type laser. So you put 8 of them in a box. I mean, I'm simplifying it. Yeah. My transceiver designers are going to kill me. But it's not as simple as just putting in a box. But you got 8 transceivers, 8 lasers, so you get 800G transmission. Now, to get 1.6, you can say, okay, why don't I do 16? There's just not enough space. So the 1.6T transceiver is being paced by a 200 gigabits per second laser, which we are working on. We have announced multiple. In fact, we've a year ago, we showcased a 200G EML, multiple types, EML, a 200G, another technology called DFB Mach-Zehnder. We are working on a 200G VCSEL. We've not announced the product yet, but it's something that we are actively working on. And to some extent, Jeff, we are going to pace the 1.6 transition because we are the ones who are driving the state of the art in lasers.
Are those lasers pulsed or continuous wave?
Well, they're all pulsed. They're okay. So let me. So the VCSELs are what we call directly modulated. basically you turn the VXL on and off, simplistically said.
Versus
The EMLs have to get, there's the modulator is built in, it's an electro absorption modulator. Yeah. So modulation is pulsing in a very, layperson kind of a. So
and that doesn't matter whether you're going a centimeter, a kilometer,
it does. Unfortunately, that's why we have all this alphabet soup of different flavors of transceivers. They're short reach. Good news is that for any transceiver, VXL-based transceiver gives you the lowest cost, and that doesn't go very long. But most of these GPU networking and AI clusters are all
connecting
they're in the smaller areas. We have some that go up to 500 meters, kilometers. Some of the EMLs can go. And the DFA Mach Center actually goes, one of the longest reach lasers that we have today.
Okay.
So
we go. Let's roll the camera forward here. So we have GPT-4 today, Gemini. We're going to go to GPT-5, and then two-mode Gemini, two-model Gemini, and then generative AI 2025, 2026, and then really we basically get to full AGI 2027, 2028. Sound pretty reasonable to you?
Yeah. I mean, we are getting ready. So we're this is each one of these. I mean, when you look at our, just from what that does to our business, right? The 800G market was in calendar 23 was 0.6 billion. In calendar 28 is 9 billion. 800G and above, right? So it's at a 70% CAGR, and I mean that's our best estimate today. But we're just. If you listen to Jensen and and NVIDIA and other such pioneers, I mean they're saying we're just scratching the surface. There's just so much of room to go.
Which gets to
in terms of applications, in terms of video, we're just getting started on video.
Which the Soros stuff is really cool.
Yeah,
that actually gets to the heart of my question, which is the growth of AI in its current form is not constrained it's not constrained by the number of people. Like I can do more with GPT and more people get on GPT, but really what we're talking about is getting to a point where these models, these systems are consuming vast amounts of information from sensors and different and vision systems, and now starting to be autonomous in their own sense.
Yeah, absolutely. Because so AI, we were actually talking about this the other day. AI, the first jump or the first fillip for our business is really datacom, right? AI directly. You put these clusters into the data center, you need to buy transceivers. But if you look at our sensing business, right, our advanced sensors are the eyes and ears of AI, right? Sensors are the input that goes into AI. Hey, Jeff, we're sitting here. Can we, somebody is looking at me from that other window. Do we know who that person is? Yeah. You go, you send your 3D sensing, you pattern match, you run it through your database, your machine learning algorithms and all of that. And then, so sensors are pretty important. Then when you look at AI, the chip technology in AI is the cutting edge stuff, right? The really leading edge nodes. And to make those leading edge nodes, you need leading edge process tools for semiconductor capital equipment. It's one of our verticals. And our lasers, optics, and materials enable those next gen tools to make these next gen chips for AI. So we have so AI indirectly drives our semiconductor capital equipment business, right? And then cooling. It's such a big deal. These chips are, it's really two problems that it's really the cooling is going to determine the performance of some of these AI solutions. And, we have a variety of products there for cooling, metal matrix composites, even diamond.
Yeah. The diamond heat spreaders is really fascinating.
Yeah, technology. I mean it's the world's best thermal conductor. It's again superlative properties. If I'm a thermal engineer, diamond. If I'm a structural engineer, diamond. If I'm an electronics engineer, diamond. It's like diamond.
Although when I told my wife that we manufacture diamonds, she didn't care about any of that.
Yeah, she said, "Can I get it?
Just give me some." Yeah. Okay, so sensors, vision, world's consuming more data. Okay, do we move that communications capability? Does that just keep moving into the device, into the GPU?
Well, I mean, the fact is that all this capacity, compute capacity, all the networking that happens in the data center ultimately will drive bandwidth, right?
Yeah.
Will drive for bandwidth. So we are just starting to track it. We do expect, we segment our communications market in datacom and telecom. So we do expect all the AI that's going into these data centers, the infrastructure, will drive needs for, will drive demand for telecom or the long haul business. But then, Jeff, I don't know whether you know, 3.4 billion people in the world don't have internet today.
That's just
isn't that fascinating?
Yeah.
There's a whole world, all those people need to get on the internet first, which means connectivity, 5G, the submarine
SATCOM
cables,
is being an
SATCOM, for locations that are, some of the rural underserved areas. That's the only way. SATCOM has been great. I mean,
we think that a lot of people think, especially in urban areas, think, oh well, if you're in a rural area, that means you're like, you're in a part of Nebraska somewhere, and there's one house for every 6 miles. Yeah. Where I live in South Florida, we're underserved with broadband, and Starlink really has become the most viable option.
Yeah.
I had to bring fiber into my house to have a reliable connection, but previous to that, we were using Starlink, and it worked great.
Yeah, no, I mean, I'll tell. I mean, you'll be shocked to hear this, but let me give you an example of high bandwidth. Right? People often say, "Hey, aren't we done with bandwidth? Do you really need more bandwidth?" So to do full parallax, high definition, holographic imaging, meaning you could be sitting in your home in Naples, and I could see a holographic high definition image of you, and I can actually walk around you and see, it's sort of, you can walk around me and do all that. You need 10 terabits per second at the user. This connection that we have, that needs to be 10 terabits per second. 6G for a mobile device will not get you there. 6G is only 1 terabit per second. And, you talked about locations. We live in the heart of Silicon Valley. I get a grand 30 megabits per second. And if we have 3 Zoom lines going, if my son and my wife are working from home, it's a challenge.
Yeah.
We've got orders of magnitude. The applications are there, and the capacity is here. There is, I'm not saying, of course, there are a lot of places where you do get fiber and high bandwidth. There's still many orders of magnitude to go.
Well, and this actually reminds me of like trying to get a cell phone signal on Sand Hill Road sometimes, right? It was always a challenge.
Oh, yeah, it still is.
If I go back to the 90s when, the early days of the internet, but really networking as a whole, we were driven by a model where the equipment providers were producing manufacturing equipment that created more bandwidth, and then the applications filled that bandwidth. Now it seems like we hit an inflection point or a pivot where the applications are demanding more bandwidth, and everybody's trying to catch up to it from an infrastructure standpoint.
Absolutely. I think it's been that way for many years now. But you're absolutely right. Remember, there was a time when, hey, what do you do with that extra bandwidth?
Yeah.
You're doing email.
Who needs 10 megabit per second?
Yeah, exactly. Exactly. It's important to our lives. There are certain places where, for medical reasons, emergency services, there's a lot of stuff that rides on connectivity. It's a must have. It's not it'll be nice to have an internet connection. No, it's like, water, and, it's a utility. You need it.
Which is, we've existed in a world where there's the datacom providers and there's the telecom providers, and the telecom providers for now a long time have really been datacom providers who have telecom as a service. Now they're fully moving into this unified datacom space.
Yeah.
How do all of the things we've just talked about impact the telecom?
We call them multi-service operators, MSOs.
Yeah.
So you have the carriers, you have the data center operators, you have the MSOs. That whole world is still evolving. But let me tell if you stick with optical, let me give you an example of how pervasive we are in terms of a component supplier. Okay, so you make a call from your phone. Yes, sure, we have a lot of content on the phone. There are some RF chips that use our substrates, etc. But it goes to a tower. The amplifier in that tower, the 5G antenna, uses gallium nitride on silicon carbide electronics, and we make those substrates. Those are different types of silicon carbide substrates than we make for EV charging and all that. It's a different type of material, but okay, so you've got some content there. Then the signal goes down to the tower, and there is an optical transceiver or a bunch of optical transceivers. So that's when the signals go from the electrical domain to the optical domain. And then from the tower, it's basically, aggregation, higher and higher levels of aggregation. Everything stays in the optical domain. Yeah. Multiple transceivers to come together, multiple those come together. So you get access, metro core, long haul. Then let's say you're making a call to someone in Singapore, so you go undersea. Mm-hmm. And then you come on the other side, and then the same thing happens and goes to a tower and pick up the phone. Jeff, if I tell you, you can build that entire link right from the first transceiver at the base of the optical tower, just with our optical components. You don't need to buy from anybody else. That's how pervasive are the switching, the amplification, the monitoring, the routing, the transmission. It's just it's and anything that we make, we are completely vertically integrated. We start at the materials. In fact, sometimes we say our raw materials are powders and gases. Mm-hmm. It's true. Mm-hmm. We start with powders and gases. So that's pretty fascinating. I don't know whether a lot of people appreciate that.
Now Next and Beyond is hosted by Jeff Nolan, produced by Carly Berghoff, and presented by Coherent.